Well, welcome back to our designer conference. This evening we're going to be having several speakers. First, we're going to start off with Dr. Andrew Snelling, and I'm going to go ahead and introduce him. Dr. Snelling completed a Bachelor of Science degree in Applied Geology at the University of South Wales in Sydney, Australia. His PhD in geology was awarded by the University of Sydney in Australia for his research on geochemical study of the Koongarra uranium deposit. Did I get that one right? Yep. Yeah, there we go. So it's exciting. Dr. Snelling has been involved in creation, writing technical articles, and being on a number of publications as well as a number of DVDs. He's been with the Ministry of Answers in Genesis for a number of years. He is the Director of Research here, as well as the Editor-in-Chief of the Answers Research Journal, a peer-reviewed journal that promotes the authority of the Word of God and our Creator, Jesus Christ. Without any further ado, Dr. Snelling.
Thank you. Well, you're going to have to switch your brains a bit again to get used to a different accent. You had the cultured British accent before, but I have to add that we Australians didn't revolt. We didn't have a chance. We were in chains. But I'm happy to say that my grandfather emigrated to Australia as a free settler. So, but seriously, it used to be a badge of honour to be related to the ones who came out in chains. That's so you could get used to my voice before we got started. I hope to take this slowly to begin with and revise a few things that you should be familiar with, although some of the younger ones should have been doing this in your studies. I want to talk this afternoon about minerals by God's design. We often think about all the biological things that are designed, but we forget about the things that are under our feet that make it possible for the biology. In fact, we geologists say the biology just covers up the geology, just get rid of it so we can see the rocks. But, whichever way you look at it, we do live on a beautiful planet and a beautiful home that shows God's specific handiwork to make it fit for human habitation, providing us with the resources and everything that we need for the life that we have here on earth. And so even what makes up the ground beneath our feet shows all the hallmarks of God's design to make it a place that was purposeful for us to live in. And of course, He built the ground out of rocks, which are made up of minerals. They're the components in rocks. So for example, you pick up a granite and you see different coloured grains of different minerals. And I'm going to show you some of those this afternoon. Now, of course, geology or earth science is the study of the earth, its rocks and its minerals. And of course, that's my background. Understanding how God made the minerals and how He designed them to make this earthly home that we live on so beautiful is akin, as was wont to be quoted, to think God's thoughts after Him. So as we move from this spectacular view of the earth from space, of course flattened out, not global, let's think about minerals this afternoon. Minerals, of course, are built from atoms. Now let's think again about what we learnt at high school in physics and chemistry. Of course, atoms are so tiny that we can't see them, and they're visualised like tiny balls of different sizes, each size with different properties. Of course, they're not really tiny balls, but we visualise them like that. And it's a very helpful model or way of understanding how these atoms behave. And of course, each different sized atom is called an element. And so we know that it has a nucleus consisting of neutrons and protons, surrounded by orbiting electrons. Okay? And that's how we understand atoms in the broad sense. Now, the size of the nucleus depends on the number of neutrons and protons in it. And the number of protons, of course, gives it the number of the element. So, for example, carbon is the sixth element because it has 6 protons. It also has 6 neutrons. So a stable carbon atom is a carbon-12 atom. and it has 6 electrons orbiting around it. Now, it's because the atoms have these electrons and protons and different numbers, gives each element its unique properties. And we've given each element, as it's been discovered, a name, and it's abbreviated with a symbol. Sometimes the abbreviation is from the English, sometimes it's from the German or Latin. Argentum, Latin for silver. Ag is the symbol for silver. And of course, chemists have constructed a table of the elements, putting them in what we call the periodic table with elements in rows and groups and columns so that we can visualise their properties being similar. Okay, so many of you will remember this from your high school days, and some of you are probably learning this in your high school studies. So, for example, on the right-hand side, we have the noble gases, or inert or noble gases: helium, neon, argon, krypton. And on the left, far left, we have the metals. We have a few more metals, the red ones there, aluminum, etc. In between, we have the transition metals, which include, in orange there, we see iron, magnesium. And then we have the lanthanide series and the actinide series to round it out. And this is a way of understanding the structure of the atoms. So, for example, all the lithium, sodium, potassium, they all have an atom that is similar in structure, but as you go down that column, you have another shell of electrons, but they all behave in the same way. And this is very important for understanding how God designed these atoms specifically so they will combine in ways to give us the minerals that we have. And I think you're going to be fascinated. So all the elements, of course, were needed. That's why God created them. And, some might be considered more important than others because they're more plentiful or needed, but they're all important. Elements that have strategic roles to play in the way God has designed the world. We're all familiar with carbon, which is basically the atom of life. Carbon is the building block of the molecules of life, and the carbon, the way it's structured, it enables you to put on the hydrogen atoms and the oxygen in chains and build chains and all these fabulous molecules that the biochemists talk about. Well, the atom for rocks, the building blocks for the common minerals that form rocks, is the atom silicon, abbreviated Si. And it would surprise you actually to realise that silicon and carbon are in the same column of the periodic table. They both have a 4+ charge. That means that they're able to have an excess of protons to attract linkages with electrons. And what this does, in the case of carbon, it allows you to hook on hydrogens and all that kind of thing. In the case of silicon, it allows you to have oxygen as its major combining atom. Now, when it comes to forming rocks and the minerals that make up rocks, there's a few elements that form the majority of minerals. The key ones are oxygen, obviously, and silicon, but aluminum, then we've got iron, calcium, potassium, sodium, and magnesium. They're the major elements to form in rock-forming minerals. Lesser extent is manganese and titanium. Most of the other elements are very rare or have a minor or trivial role, but it's also an important role, as we'll see in a moment. So there's only a few elements that we have to deal with, and when we look at the abundance of these elements, you'll see that area that's hashed in green. On the left-hand side, the scale is abundance in terms of atoms of the element per million atoms of silicon. Okay, and then the atomic number is on the horizontal scale. So all the low atomic number elements are the ones that are in great abundance compared to silicon and form the rock-forming minerals. It's only when you get down to the right-hand side that you get a lot of rarer elements. So again, this highlights God has designed these atoms to combine in ways that will produce minerals. Minerals that are different from one another, different properties, different shapes, different colours. Lots of variety. As I say to people, God loves variety and beauty because he made so much of it. And we can marvel in his handiwork even in the minerals in the rocks beneath our feet. Now the silicate minerals, those minerals that are based on the element silicon, make up 92% of all Earth rocks. That doesn't include the element carbon, which of course is present in calcium carbonate or limestone. Now when you travel around here, you see so much limestone in the road cuts, so you think there's heaps and heaps and huge volumes of limestone. Well, that pales into insignificance. That's in the 8% of the rock-forming minerals. 92% are made up of these minerals based on the element silicon. So you can see why we need to go in a little bit further into this, how God did it, or the structure of design that he used. And the structure, the basic structural unit is called the silicon tetrahedron. Remember I said the silicon atom is a 4+ charge. It's able to hook on around it 4 oxygen atoms. And you can see from this diagram that effectively it forms a tetrahedron, which is a triangular pyramid. And these are different ways of depicting it. And every geology student who wants to learn about rocks has to first of all learn about minerals, and this is drummed into us right from the very start. The silicon tetrahedron. Si, that's the element silica, O4, that's 4 oxygens. It's the basic building block of these minerals. And the way these tetrahedra are stacked or combined with one another gives us the different crystal shapes. And what other atoms are involved in hooking them together helps not only provide the shape, but also the variations of colours within the different mineral groups. And we'll illustrate this. So the different silicate minerals are constructed according to how these silica tetrahedra, these triangular pyramids, are linked to one another and stacked. They can be linked by sharing oxygen atoms at the corners to produce chains or frameworks. And sometimes the aluminum atom is substituted in. But they're also combined. The individual tetrahedra and chains of tetrahedra are linked by atoms of the other major elements: iron, magnesium, potassium, calcium, sodium, those ones that I said are very important. And that produces the variations. As I said a moment ago, the way the tetrahedra are combined produces the different crystal shapes, and you'll understand this very graphically in a moment. And what elements are linking also result in the different colours that we see. Because the way they're linked, the colours are not intrinsic to the atoms, but it's because of the way light interacts with the crystal lattice that produces the colour. So slight differences because of different atoms means the light that's reflected off the mineral and comes through the crystal lattice will give you the different colours. So here's the different groups, and I've listed these for you in the notes. You've got single tetrahedra, we call those NEOSILICATES. Couplets of tetrahedra, they are SOROSILICATES. CYCLOSILICATES, that should be obvious. These are rings of tetrahedra. INOSILICATES are the chain silicates, either as single or double chains. The PHYLLOSILICATES are the sheets of tetrahedra. And finally, we've got the TECTOSILICATES, which are frameworks of these tetrahedra, these triangular pyramids. Now, I hope I haven't lost you already, but it is really not that hard to understand once you've got those basics. Because now what I want to do is to go through these groups, showing you how these tetrahedra combine and how it affects the crystal shape when you add in the different elements, the different varieties you get, even of the same mineral. And it's really fascinating to see the way God has designed these minerals. And let me add in here, these minerals all have practical applications. The mineral quartz, which we'll come to, most watches have quartz. The mineral garnet, for example, that we'll see in a moment, is they're finding some staggeringly wonderful properties for certain high-tech applications. And the engineers are discovering this all the time, that the way God has designed these minerals and their properties enable them to apply them to real-world human problems. And all they can do is copy God's designs. Sometimes they'll make the same mineral with a particular element in it because they want the same structure and the same properties. Well, with that, let's just illustrate the isolated silicate structure. The first one there is just those tetrahedra linked to one another by other elements. The single chain, the double chain. Let's get familiar with some of these terms. As olivine is the single chain. Pyroxene, or in English we say pyroxene, but in American you say pyroxene. Amphibole is the double chain. Then we've got the mica and clay groups are in the sheet silicates or phyllosilicates. And the framework silicate structure is quartz and feldspars, which account for more than 50% of the volume of rocks that we find on the Earth's surface. So let's go through these groups. First of all, the single tetrahedra. You can see there on the left, two of these tetrahedra, their bases are linked to one another. Between them, you have atoms of magnesium and iron. And the mineral is olivine. Now, you might not be familiar with olivine, but if we were to look at the whole Earth, it's probably the most prominent mineral in abundance because it makes up much of the interior of the Earth, because it has such a tight structure, olivine. And here's another way of illustrating it. These diagrams might look complicated to you, but just think of these little triangular pyramids, these tetrahedra, and those blue atoms on the left there are the iron and magnesium that hold these isolated tetrahedra together. What does olivine look like? There it is. It has a gem variety called peridot. Now, I'm going to mention gems every now and again because the ladies are familiar with some of these gems. Peridot, it's actually the mineral olivine. As I said, much of the Earth's mantle is made up of the mineral olivine. And it's a beautiful green, glassy mineral. And why you can get pure magnesium olivine, and you can get pure iron olivine, and you can get in between where you've got a mixture of magnesium and iron atoms that are linking these silica tetrahedra. That's what we mean by Mg, Fe. You've got two magnesium and iron that are in various proportions. In geology, in the mineralogy, we call that a solid solution series. You've got the iron end member and the magnesium end member, and you've got substitutions of atoms all the way through a continuum of compositions. So I'm trying to introduce you to these terms because it's really fascinating, these minerals, but it's so foundational to understanding how God built the earth with minerals making up these rocks. Okay, so these are neosilicates, these single tetrahedra. The next group is the garnet group. Again, you'll have heard of garnet as a gem mineral, and it's one of the minerals that's actually one of the most astounding minerals for geological studies that geologists are finding is so useful in understanding what happens in rocks because it records so many details. But the engineers are now finding this has so many properties that are useful. So the garnet group, now it has the same structure, mineral structure, but now we've got a whole series of combinations. We can use magnesium, we can use iron. Iron comes in two varieties. You've got 2+ and 3+. You've got aluminum, you've got manganese, you've got calcium. You've even got chromium in uvarovite. So pyrope garnet, almandine, spessartine, grossula, andradite, and uvarovite. Let's have a look at some of these. They're spectacular. That's the common garnet mineral called almandine. These crystals are called dodecahedra. And if you look up close in the next one, you can actually see the edges aren't sharp, there's a bevel. So you've got a 16-sided crystal, and where the faces connect, sometimes you've got actual beveling. Let me show you another example. This is andradite. See the beveling there? I mean, the beauty of these crystals, and it's all because of the atoms and the way God designed those atoms so they will link in certain ways with combinations to give you the colours as well as the crystal shapes. So these are all these single triangular pyramids or tetrahedra linked. Then another andradite, crystal of andradite, pyrope. Pyrope is often found with diamonds, comes from deep inside the earth. Grossula, it's the calcium aluminum garnet. And then another crystal display of grossula. Spessartine. Look at this one. This is this is another spessartine, and this is uvarovite with the chromium. Now, God could have just as easily made a garnet, made it all the same colour. But no, as I said, God loves variety, he loves beauty. I mean, look at everyone in this room, with all of us a variety, aren't we? No two of us are the same, and that's wonderful. And it's like that with the minerals, with the way he's enabled them with the atoms combining to give you these colours. And we can enjoy them. Garnets, God's handiwork. Other neosilicates, that is single tetrahedra minerals, are zircon. You may have heard of zircon, zirconium silicate. It's an important mineral that geologists use for uranium, lead dating of rocks. Then there's the aluminosilicate group, andalusite, kyanite, sillimanite, topaz. That comes as a gem. And staurolite. Let's have a look at some of these. That's zircon. The one on the left is a crystal that's beautifully formed. The one that's on the left, the one on the right is actually a crystal under the microscope that's fallen out of a granite, that's been extracted from a granite. Here's another crystal of zircon. Andalusite, that's an aluminosilicate, aluminum and silica. And it comes in, the aluminosilicates come in three forms depending on the temperature and pressure. We know that they can form under different temperatures and pressures. So you've got andalusite, you've got kyanite, which is the high pressure form, which is beautiful blue colour. Imagine it's the same chemical composition, but there's just a slight variation in the way it's combined because of the temperature pressure conditions. And then we've got sillimanite on the left, and staurolite, if you add in some iron to confuse things. And staurolite crystals, the way you can often find them is they come in these crossed twins. Two crystals actually cross, and that's fascinating. But here's what I said: different pressure, temperature. The andalusite is the low pressure, low temperature form of aluminosilicates. Kyanite is high pressure, sillimanite is high temperature. And geologists have experimented with these minerals to show that the crystals cope with different temperatures when they form under different temperatures and pressures. Next we come to couplets of tetrahedra. These are the SOROSILICATES. Now, this is where instead of you have the isolated tetrahedra, now one oxygen atom is shared at the apex of the two triangular pyramids. Okay? So you've got two triangular pyramids linked by a common oxygen atom. The chief mineral in that class is epidote. And again, epidote can come in gem forms. There's a whole class, there's a whole group of them, depending on which atoms are involved in combining these couplets of tetrahedra. There's epidote, zoisite, clonozoisite, tanzanite, allanite, etc. And you can see that allanite has a very complex chemical formula because it's got some of the rare earth elements in it. Epidote, there it is. It's a greenish mineral. Here's another photograph of epidote. By the way, geologists have to learn these minerals so that you can actually pick up a sample and identify it straight away. So you really got to get up close and personal with these minerals and get to know them. Zoisite, you can see on the left there's a slightly different colour because it's in the background of the rock material behind it, whereas in its pure crystalline form it has a glassy green colour. Then we've got clonozoisite, allanite. It's a very important source of rare earths. Well, let's move on to rings of tetrahedra, the cyclosilicates. Now, this is where the tetrahedra share common oxygen atoms at their corners, but you have 6 of them in a ring structure. 6 of them in a ring structure. Now, imagine now what's going to happen when you've got a ring structure. What sort of shape are you going to get in your crystals? 6. 6-sided. Hexagons. Ah, yes. Again, lots of variety. So we've got the axonite mineral, we've got beryl, the gem variety is emerald, we've got cordierite, and we've got tourmaline, which also has gem varieties, which is a fascinating mineral, as you'll see in a moment. That's crystals of axonite. You actually get boron or borate in the formula of these minerals. It gets into the act. Axonite. Then we get on to beryl and emerald. Beryl is the common variety. It's a beryllium aluminum silicate. And the gem variety, of course, is emerald, which is a very hard mineral. Again, it's a gem quality mineral. In fact, emeralds can fetch very high prices. So here's again some examples. Notice the hexagonal prism. Because of the ring structure, it's affected the shape of those crystals. Nice hexagonal columns. Here's another version of beryl. Sometimes the colours are due to slight contamination with other elements. I'll show you a vivid example of that in a moment with another mineral in this group. So there's beryl, and there's the aquamarine, which is a variety of beryl. By the way, this mineral, back in about 50 years ago, they were looking for beryllium for some of a combination in metals to make special metals for spacecraft. And it was a sought-after mineral at that time because it was a source of beryllium. Emerald. There's a gem version. Here's another gem version. Then we've got cordierite, which is not a mineral you'd be familiar with, but it forms often in metamorphic rocks, that is under temperature and pressure, and sometimes in granites. Tourmaline. Now, this is an interesting mineral. You can see it combines a lot of interesting atoms in various amounts. Lithium gets into the act here, as well as boron, I should say. And so we've got tourmaline there on the left is eblerite. The one on the right, you can see it's got different candy cane colours because of different contaminating elements. And the ones on the right come from Brazil, and they're very highly prized. They fetch a high price on the on the market because they can be turned into gems. Here's another one too on the left. That's a variety that people go for as well. Well, next we come to the chain silicates, the INOSILICATES. The single chains are the pyroxene or pyroxene, depending whether you're in Australia or the US. And it's a very common mineral in basalt, or basalt in Australian and English. And actually it's a common mineral in meteorites, enstatite. There's a whole class of meteorites called the enstatite chondrite meteorites. And here we see, again, substitutions in solid solution. So we've got the enstatite orthoferrocellulite series, we've got the diopside Hedenbergite series. Augite in that series is the common pyroxene or pyroxene that's found in basalts. And then we've got the sodium pyroxene series. Jadeite is the basis of the mineral jade. And spodumene, which is a lithium pyroxene. And this is what I mean about solid solutions. The geologists, mineralogists draw these triangular diagrams. And on the right, bottom right, we have the ferrocellite end member. On the bottom left, we have the enstatite end member. And we have all these substitutions in between. A whole series of compositions, substitution of the atoms of iron and magnesium. And we can go the other way towards substituting calcium. And halfway up there, you've got Hedenbergite and diopside. We can do the same sort of triangular diagram for other elements, for sodium aluminum, for sodium iron, for calcium, magnesium and iron. And so you can plot these different compositions. Here's these chains. You can see it very clearly on the left, where you've got the triangular pyramids, tetrahedra sharing a common corner, oxygen on a common, and in a chain where the tetrahedra offset, alternately offset. The way they're stacked is slightly different in enstatite to diopside. We draw these fancy diagrams so we can understand the crystalline structure very slightly according to the way the crystals, the atoms are stacked. But this is very important when you're trying to identify a mineral with a hand lens, in-hand specimen, or even under a microscope. So here's how these chains combine, slight variations in different types of pyroxenes, but let's have a look at the varieties we get. Enstatite, which is the magnesium end member, and you can see there you get a pure green crystal. This is what pigeonite looks like under the microscope. Some of these photographs are actually taken on a geological microscope. Then we've got diopside, which is a calcium-magnesium pyroxene. And we have the white variety, we have the green variety. Hedenbergite, again, different, a darker green. Augite, the common black pyroxene in basalt. It's the commonest of these pyroxene minerals. But sometimes, depending on what substitutions you have, element substitutions, you get a greenish tinge to it. Here's jadeite, from which we get jade. And aegirine or acmite, which is a sodium iron, 3+ iron, ferric iron. And here's another photo of another crystal. And finally, the lithium pyroxene, spodumene. And the calcium pyroxene, wollastonite. Let's move on to the double chains of the INOSILICATES, the amphibole group. Okay, and we've got the Coming Tonight series. We used to have a joke about that. Are you coming tonight? The grunerite and Coming Tonight, the tremolite series, tremolite, actinolite and hornblende. Hornblende is the most common amphibole. We find it in granite and we find it in metamorphic rocks as well. And then we've got the sodium amphibole group, glaucophane, riebeckite, asphadsonite. And again, the way these silica tetrahedra are linked up, we've got two chains that are now linked into a double chain, two single chains linked in a double chain, which affects the way the stacking is and the way they're linked with the different minerals. But again, we can plot solid solution series where you go from grunerite through to cummingtonite, where you add some more magnesium, and down the other end you've got anthophyllite. You add calcium, you've got tremolite, and there's a solid solution series between that dark area between tremolite and ferroactinolite, and in the middle is actinolite. And so we find that sometimes, notice, you've got those dark bands, that's where you've got a solid solution substitution. Where you haven't got it means that there are areas where you don't find those substitutions. So there are limits to the substitutions, which again reflects the way the atoms, God created the atoms with their properties. So anthophyllite, I want you to notice a common theme with a lot of these minerals, okay? And you'll see where I'm going in a minute. Anthophyllite. Okay, then we've got this smaller, thin crystals of anthophyllite. And another picture of anthophyllite. Then we've got cummingtonite. Notice these fine crystals. What do they remind you of? Grunerite. That's not so good a photograph. But then we've got tremolite. And tremolite, which is a calcium magnesium. And actinolite. Look at these tiny needle crystals. Then we've got hornblende. By the way, that comes from a German mining term. Horn, of course, is a sheen, a horny sheen, a horn, the sheen on the luster on a cow's horn. And blende is a common German mining term for a mineral. Glaucophane. Now, this'll give the game away. Riebeckite. These are the asbestos minerals, by and large. And asbestos, of course, has important properties. You can make it into cloth, which helps to protect people in a fire situation. But, of course, those fibres are not good to breathe. And it causes asbestosis, where people get emphysema because they can't breathe, because those fibres have clogged up the alveoli in their lungs. And then we've got riebeckite. That variety is called crocodilite, which actually can be made into a gem called tiger's eye. As soon as I mention common names like that, everyone goes, yes, okay. But it makes sense. You can see where this all fits in. Asphadsonite. Now, another interesting property which is important for geologists, you've got two black minerals in a rock. Is it a pyroxene or an amphibole? Well, here's how we know. Because the single chains stack in a certain way, the crystal breaks along surfaces called cleavages. For pyroxene, because it's a single chain, the angle between the breakage is 87 degrees or 93 degrees. It's almost at right angles, but not quite. But because when you've got an amphibole, you've got a double chain, it changes the angle to 60 degrees or 120 degrees. And so as soon as you see a black mineral in hand specimen, with your hand lens, you can see the angle of that crystal faces. You know whether it's a pyroxene or an amphibole. And you also see it in thin section in a microscope because you can see the way the crystal shapes are under the microscope. All important clues that the geology students have to learn. Next, we get to the PHYLLOSILICATES, which are the sheets of tetrahedra. And here we come to an important group of minerals, two groups, the micas and the clays. And these minerals have very important properties that are very useful to man. You mightn't think so, clays. Some of you ladies in your gardens mightn't like the clays, but clays have some very important properties. You mightn't realise it, but the paper you're writing on actually has a clay filler in it. Very important in paper production. We'll come to that in a moment. So man has harnessed the properties of these minerals because of the way God created them, with properties that would be useful for us to use. They were designed specifically, and we've discovered God's designs. Okay, now we have these sheets. Okay, all these triangular pyramids or tetrahedra are linked in sheets, and these sheets are stacked on top of one another with linkages. Now, what does that tell you? It means that it's easy for the sheets to break apart. And that gives micas their unique property. They cleave in this direction. They're sheet silicates. Okay? And so we have the mica group, biotite, which is the black mica, which is found in granites, and also muscovite, which is the white mica. In fact, before we had, high temperature glasses to put on our front of our fireplaces, 60, 70 years ago, they used white mica as the window in a wood stove because of its temperature-resistant properties, but also you could actually still see through the white mica. Muscovite, phlogopite, lepidolite, margarite, and glauconite. And then there's the chlorite group. There's a whole suite of terms in that mineral. Now, again, the way the sheets are stacked is slightly different for biotite and phlogopite compared to muscovite. There's just slight differences. This is biotite. It actually looks black when it's against other rock material, but when you get a very thin sheet of it, it can be brownish in colour. So that's biotite, another biotite crystal. Now, because these sheets stack up like the pages in a book, and you can peel them apart, we call that a book of biotite sheets, a book, because you can peel apart like pages. By the way, for those of you who remember, it's in biotite that we find the radiohalos. And we can find the right section to look at by peeling off the biotite flakes till we get down to the centre of the radiohalo. This is what biotite looks under the microscope. By the way, this is not plain light. This is called polarised light, where you actually, when you've got sunglasses, but if you get two Polaroid lenses and they let the light through in different directions, if you get two of them together like that, they cancel out and it's black under the microscope. But the minerals have the property of being able to rotate the plane of light by different amounts for different minerals. So under the microscope, you can actually identify minerals by their colours because of the way they've reacted with the light. And biotite, you can see these beautiful coloured crystals. They're sheets, flakes, under the microscope. Muscovite is the white mica. Again, that's a book of sheets that you can peel apart like pages of white mica or muscovite. Then we've got, there it is, you can sometimes get the way it's grown in the left-hand photograph. Of course, the sheets, the little sheets have grown at angles to one another. A fascinating rosette of muscovite flakes. On the right is a typical muscovite in what we call a pegmatite, which is a end-member variety of granite. That's what muscovite looks like under the microscope in polarised light. And then we've got phlogopite. Phlogopite's an interesting mineral. It also is found, it's very rare, but it's found in the host rock, the rock that hosts diamonds. I mentioned pyrope garnet and phlogopite. Now, these are two important minerals. If you want to explore for diamonds, you've got to know what type of rock diamonds come in. If it's got a rare mineral, and you find that rare mineral in the gravels in a river, in a stream, you know it's coming from near a source of diamonds. And that's how we discovered diamonds in Australia, when no one said there were diamonds in Australia. We now have the world's largest diamond mine because of a discovery like that. Lepidolite is the lithium aluminum mica, which comes in a variety of colours depending on the substitutions of different elements. And finally, glauconite, which is a common mineral in some of the ocean floor sediments. Then we have two other groups, the serpentine group, which comes in a variety of forms, antigerite, chrysotile, and lizardite, and then the clay mineral group. And again, it's the way the sheets are linked and oriented with one another. Serpentinite, you're probably familiar with it. There's a rock specimen, but on the right you've got a polished slab. Seen slabs like that in some buildings as a cladding stone? That's serpentinite. It often can be used as a cladding for buildings, to beautify a building. And we can admire people use granite, for example, with its crystals on a bench top. And so that we can enjoy these minerals. Then we go on to the clays with their unique properties. The way the sheets are connected with one another and oriented with one another. Kaolinite. That's the mineral they use on the paper that you're writing on. It's a filler. They can use it in paints as well to give it its stiffness and also its colour. We've got montmorillonite. And we've got vermiculite. Some of you might have heard of vermiculite. Some of these clays are very important for the petroleum industry, for the drilling muds. When they're drilling for oil, they want to have some of these pure varieties of clay minerals. Another stacking arrangement is in the mineral talc. That's right, we get talcum powder from the mineral talc. It's actually a sheet silicate, and it's crushed to form that talcum powder. So you're shadowing yourself with a mineral when you put the talcum powder on after a shower or a bath. And finally, we come to the tectosilicates, which are the frameworks of tetrahedra. This is where all the tetrahedra are linked at all the corners in a framework, and the pure one, of course, silicon dioxide. Remember, these are triangular pyramids of silica, SiO4. When you link them all up and you've only got silica and oxygen in this framework, you've got the mineral quartz, which is the glassy mineral that you see in granites. It's the same material in a pane of window glass. It's quartz, silicon dioxide. The other main tectosilicate is feldspar, and feldspars account for 50%, are present by volume, 50% in abundance in earth rocks. So here's these groups. We've got the quartz group, then we've got the feldspar group. We've got the alkali feldspars, primarily based on potassium and sodium in a solid solution series, which I'll show you in a minute. And then we have the plagioclase feldspars, which are sodium and calcium substitutions. Here again is this diagram, so we can go back to this abundance. The tectosilicates make up 63% of the total mineral abundance in Earth's rocks. Plagioclase feldspar and alkali feldspars make up just over 50%. Quartz makes up 12%. So these minerals are incredibly important. They are the main minerals. Quartz, alkali feldspar and plagioclase are the main mineral in granites, the main minerals that make up granites. So here we have quartz crystals, often seen with beautifully terminated points. You get a little bit of contamination and you get smoky quartz. These crystals often grow in cavities where they're free. The water-filled cavities with the chemicals in them has allowed the crystals to grow in freedom to make these beautiful crystal shapes. Then you get a little bit of another element or two in there, and you get rose quartz or jasper in its impure form. Then you get nodules that you break open, that contain a purple variety of quartz called amethyst, gem. And that's just a little bit of iron and aluminum in there. Then we get a yellow variety, that's citrine. Ladies are familiar with some of these because they're turned into gems. And then we've got agate and chalcedony. These are milky varieties. And a very famous Australian variety, opals. If you don't get Answers magazine, you better get it because the next issue will have an article on opals. Why is it that nearly all the world's precious opals comes from a particular area in Australia? Get the next issue of Answers magazine to find out. Why do we have the beautiful colours? Apart from us Australians being colourful, of course. But opal is a variety of quartz. Now we come to the feldspars. Remember, you've got on the left there, you've got a triangular diagram. You've got calcium aluminum silicate at the top of the triangle. Down the bottom left, you've got sodium aluminum silicate. And the right-hand side at the bottom, you've got calcium aluminosilicate. The alkali feldspars make up the substitution from potassium down to sodium. And the plagioclase feldspars make the solid solution series substitution from sodium through to calcium aluminosilicates. Notice the part of the triangle where you don't get substitutions. It's only along the edges where you get the pure end member substitutions. And that's because, again, of the properties of the atoms that only allow them to combine in these certain ways. So microcline is one of the potassium feldspars, aluminosilicates. Beautiful white crystals. But as soon as you introduce some impurities, you can get some varieties. Where my wife grew up was a silver lead zinc mining area. And the microcline there, the feldspar there, had lead in it, and it was a beautiful green, a very, very rare variety. But it was because of the contamination that it gave you that colour. Here's the pink orthoclase potassium feldspar that most of you will know of. If you go to Yosemite National Park and you go up on the Tuolumne Meadows and you look at the granites up there, you'll see these large pink crystals. That's the orthoclase feldspar, potassium aluminosilicate, one of these framework silicate minerals. Sanidine, we're getting a little bit of sodium now substituted in it, and finally we get the total substitution, it's called an orthoclase. Then we move on to the plagioclase series. By the way, that's what plagioclase looks like under the microscope. See all those little streaks? That's where the crystal is actually doing this. It's actually oriented slightly differently in the framework, and it forms these twins, multiple twins. And under the microscope for a geologist, that's a dead giveaway to identify this mineral. So that's plagioclase. And plagioclase goes from sodium down to calcium with a substitution in between. So you've got albite is the pure sodium end member, oligoclase, andesine, labradorite, bitonite, and northite is the pure calcium end member. Have a look at some of these. Albite, whitish, creamish. Oligoclase, you now get a little bit different. It's got the same sheen but a slightly different colour. Andesine in the middle. And we've got labradorite. On the left is a hand specimen. On the right is a polished building stone. Have you seen crystals like that on some buildings? Sometimes you'll see, they'll call it black granite in bench tops, but it's not actually granite. It's actually gabbro, which is the equivalent of a basalt, but it often has these labradorite crystals in it. And we can admire this. Every time you chop the potatoes or the carrots, you can admire the minerals in your bench top and remind you that God designed these so you could enjoy them while you're working in the kitchen, ladies. Labradorite and bitonite. And finally, anorthite. Well, having been through all those minerals, the way these tetrahedra, first of all, the silicon atom combining with the 4 oxygen to create this tetrahedral unique structure, and the way that combines to form the different minerals reminds us how clearly designed God made the silicon atom to be the very basis of what we walk on the ground that he created when he formed the earth, on which he then put the plants. Remember, he made the dry land on day 3. He prepared the rocks before he put the plants there on day 3. And so he designed these silica tetrahedra to combine in varieties of ways to produce minerals with different properties. And as I said before, the engineers and the material scientists are still finding out the way they can use these different minerals, and the way if they make them artificially, they have to copy God's designs to get it right. And the beauty of the different colours and the crystal shapes are actually a bonus. I mean, God could have just made, as I said, plain old garnet. But no, he made it with different elements to substitute to produce different colours, because he's a God not only of creative power, but he loves variety, he loves beauty, and it's clearly displayed in the minerals that he's created. And he's given us a world to enjoy, but a world to use. And we've discovered how these different minerals can be used in the service of man under the dominion mandate that God has given us. So, as we close, Earth, our home, its minerals, their variety and beauty, were designed by God to combine into rocks, and they all proclaim his creative power and handiwork. Thank you very much. Just as Bodhi comes up, let me just mention a few of the resources that have